Last time on ProTech, I showed you how voltage, resistance, and current interact. We learned that when resistance in the circuit increases, current in the circuit decreases, and the component operated by the circuit won't function as it should if it functions at all. I also shared that many of the faults that you're trying to diagnose are caused by these changes in resistance, and I shared a few examples. Well, today, I'm going to show you how to find those faults. Hi, I'm Pete Meyer, and this is Cardone ProTech. The Cardone ProTech series is produced in partnership with Motor Age, America's oldest trade publication for the automotive professional. Last time we explored what happens when you add an unwanted source of resistance somewhere in the circuit. We kind of knew what to expect from Ohm's law, didn't we? If you increase the resistance, the current goes down. And we know that due to the reduced current, the component in the circuit is not going to be able to function as it should if it functions at all. But how do we find where that source of unwanted resistance is? But we have a friend by the name of Kirschoff that gives us the information we need to develop a diagnostic strategy. Kirschoff's law says, in part, that all available voltage will be consumed by all the sources of resistance in the circuit. For our purposes, it tends to build on what we learned in Ohm's law, that it takes 1 volt to push 1 amp through 1 ohm of resistance. Kirschoff just takes that a little bit further, teaching us that everything in the circuit has some form of resistance, and all of it's going to take its share of the voltage that we started with. So by the time we get all the way through and back to the battery, there should be no voltage left over. So what do you say we try Kirschoff's law out for ourselves and see what he was trying to tell us? If we start with the circuit operating and the light is on, we show 11.74 volts in the battery that's powering our little demonstration here. And yeah, before you put in the comments that that's low, it is, and I wouldn't want that to be that level if I was testing it on the vehicle. But for our purposes in explaining and understanding Kirschoff's law, this will work just fine. Remember what he said? That all the sources of resistance in the circuit will consume all the available voltage. So what that means is if we start at the positive side of the battery and work our way around back to the ground side of the battery, we should see these little sources of resistance being, or voltage rather, being used as it crosses each available source of resistance. What do you say we give that a try? We're just going to take our positive lead and we're going to move that to the very first fitting we have there. That's going to simulate the point between the battery post and where the cable connects, a very common source of problems. And you can see that we have lost some voltage, not much, maybe about 100 millivolts, but that's all I would expect. Because remember what we talked about before? The biggest source of resistance, the single largest source of resistance, should be what? The load, the component that's doing the work. Yes, everything has some resistance, but it's minimal when compared to the load, and it just shows you that's a good example of that, just 100 millivolts. Now what do you say we kind of skip ahead and we'll come right to this side of our part of our diagram marked fuse, and you can see a much larger drop. Now we're at about 11.25 volts, so that's about 500 millivolts total that we have consumed from here to here. Again, Kirschoff's law stated every source of resistance is going to take its fair share of the voltage supplied. So by the time we get to the end, when you combine them all together, it should have used all the voltage. Let's keep on going. Now we're going to move our meter lead right up next to the load, as close as I can get it. Now here I'm reading 10.95 volts. That's about 800 millivolts that I've lost from here to here. But I still haven't lost a significant amount, have I? It's still showing up in those little bits and pieces, those little snack bites that all these sources combined are taking up to get from here to here. Now let's see what happens when we move to the other side of the load. But let me ask you, if that's supposed to be the single biggest source of resistance, what do you think we should expect to see? Well, let's find out. Now I'm just going to move my test lead to the other side of the load, and wow, look at that difference. From what, 10.9 to only about 600 millivolts left in the voltage supply that we started off with. That is a huge drop. Hey, that's what we call it, voltage drop. Every time we use some voltage to get across a source of resistance, the difference between what went in and what's coming out is the amount of drop in that leg. Remember, voltage is measured between the meter leads, so in this case, from here to here, across that load, we lost over 10 volts from what we started with. That's a significant amount. But notice we still have some left. Well, why do we have some left? Because we still have little mouths to feed on our way back. So let's keep working our way back to the battery. We'll come to this side of the switch first. About 570 millivolts. Now we'll go to the other side of the switch. About 530 millivolts. So we dropped about, what, 50 millivolts or so between there. Now we'll continue moving our way along. We're going to go ahead and skip a little bit. Let's hit somewhere in the middle. Now there's only about 300 millivolts left. And now we're going to come right where we started before, that simulation between the battery cable connection and the battery post itself. And look at that, we're down to about 20 millivolts, almost nothing. Where would that other 20 millivolts go? That little tiny source of resistance between my two meter leads, that's where that's being used. Now, as I said before, what we saw across the load, across all of the sections here for that matter, is called voltage drop. And that's a testing method that we can use to help us find the source of unwanted resistance in the circuit. But before we do that, we could see how it dropped as we went around, so we've proven Kirschoff's law. But how do we know how much voltage drop occurred in any one particular part of the circuit? Well, we can do that by letting the meter do the work for us. So what we're going to do is we're going to set the meter up a little bit differently, and we're going to try something similar to that test one more time, all right? So let's move our negative meter lead now. And we're going to use that as the test lead. And I'm going to place my positive meter lead back on the battery. Now this is my test lead. Now I want to know how much drop I have in the circuit from here to here. So let's go ahead and place our meter lead as close to the load as I can get. It's important to be as close to the load as you can get in order to test the entire circuit path. Anything that's not between my meter leads is not being checked. Now take a look here. We got 700 millivolts. That's the amount of actual voltage drop that I have from here to here. Is that similar to what we started off when we were looking at it just a moment ago? Between the 11 and some change and the 10.9, right? That was a little bit more, maybe a volt or so, but very, very close to what we're looking at in terms of drop. Now, this makes a great testing method, don't you think? If I had a source of unwanted resistance, well, that would be another mouth to feed. According to Kirschoff, it would take away from what I'm getting here. Well, we'll take a look at that in a moment. Now, if I want to check the ground side, I'm going to do the same thing, only now I'm going to move my ground lead, my negative lead, to the ground post of the battery and use my positive meter lead at the ground side of the load as close again as I can possibly get it. And again, you see a similar result, about 600 or so millivolts. That's the voltage drop that we have left to take care of all these little sources of resistance getting back to the battery. Remember, it's between my meter leads. That's where that potential lies, okay? So that's what it takes to feed all of these guys. The 600 or so millivolts we saw earlier on the positive side, that's what it takes to cover all of these guys. The load's all that's left over, okay? Now, like I said, this can be a very valuable testing method. This is telling me that this is a fairly normal source of drop to cover all the normal things I have in a circuit. Nothing unusual there. But what about the thief? Well, that could be where the problem comes in. Let's see how it applies doing a real voltage drop test to find a problem. And like it said on The Wizard of Oz, pay no attention to the man behind the curtain as we set the board up for our next demonstration. And I want to encourage you, do the same thing in your shop. After you see this video, watch it a couple of times. Get a good feel for the concepts that we're showing you today. And then go back to the shop, grab some wire, grab a couple of light bulbs, do what we're doing here until you make those measurements second nature, until you make that testing procedure your own. And then you're going to find yourself able to face even those challenging electrical problems and get through them a lot easier than you may be doing now. So here we go. Obviously got a problem. Bulb is very dim. We know there's something going on. Ohm's law taught us that if I have extra resistance in the circuit, resistance goes up. What happens to current flow? Current goes down. And if the current is not enough to operate that bulb, well, that's the result. We see a component that either is working poorly or not working at all. So it's an indication that we do have a problem in the circuit. I want to find where the problem is, though. So the first thing I'm going to do is I'm going to check the positive side of my circuit. So I'm going to put my positive meter lead at the battery. And where does my negative meter lead go? If you said as close to the load as possible, you're absolutely correct. Oh, you see anything weird? 5.97 volts, 5 volts, 980 millivolts. That's a huge amount of drop. In other words, something's telling me that this section of the circuit is consuming almost half of what I have available. And that's unacceptable. That's telling me that there's something going on that side that shouldn't be there. That's the side of the circuit that has the problem. That's the side of the circuit making the bulb go dim. How do we find it? That's easy. Use places in the circuit that are fairly easy to get to and start working your way back towards the battery with your negative meter lead until you see the reading return to normal. So let's see what happens when we do that. We'll go here first. Make a difference? Nominal. It's still reading way over 5 volts, so that's not it. Next. Still not it. Still working our way back. And we continue working our way back until we want to see that meter return to maybe a few hundred millivolts. Still not there. All right, next stop. Oh, okay. That's a lot better, isn't it? We got about 150 millivolts. So that's telling me I just passed wherever that source of resistance that's requiring 5.5 volts or more to work in order to get that current pushed through it. I just passed it. And it's going to be between where I'm at now and the last test point that I used. Now in this case it's pretty narrow, pretty easy to find, but if you find yourself on a vehicle, at the very least you're going to have an idea. It's between this point and this point. And if you played baseball, then you remember how you used to hotbox a runner. You know, the two first baseman and second baseman, they would catch a runner in between them and they would throw the ball back and forth, working themselves closer and closer until he finally caught the runner in between them. He had nowhere to go and they could tag him out, right? Same thing here. We're just going to work our way now back the other direction until we see that meter reading go bad. Smaller increments though this time. And then we're just going to keep homing in until we find exactly what's causing the problem. And I know that sounds easy, but you know what? It really can be exactly that easy. Now let's see if there's other problems that we can try to figure out using this method. Now, let's change it up a bit. Okay, Dorothy, what is your wish? Oh, I just want to go home to Kansas. Me and my little dog Toto too. No, forgive me that, guys. I know that while I'm moving these things around, I just want to kind of keep you entertained. All right. Now, same issue. We have a load that is not functioning the way it should. So we're going to start with our very first test. Remember that what that was? Positive is going to stay on positive. Negative is going to become our test probe. We're going to go as close as we can to the load. We have to check the entire circuit. You always reference the battery. You always leave a lead there. And you always get as close to the load as you can so you can check the entire circuit path. What else do we have to make sure is happening? The circuit has to be on. Current has to be flowing. If the circuit's not on, there's no reason to have voltage drop, because drop does what? It's actually what's causing the electrons to get pushed through that resistance, right? So that's why we have voltage drop to begin with. That's not going to happen if there's no current flow. But I want you to notice here in the meter, we're reading about 500 millivolts or so. Now, I get asked a lot, what's normal voltage drop? And I'm going to tell you, I have some general guidelines I go by. A circuit like this, that's kind of a little bit on the high side, but you know what? Don't quibble over a few tenths of a volt. If you're going to see a problem with voltage drop, you're going to see it like we saw it earlier. It's going to be 5.9 volts. It's going to be 1.7 volts. It's going to be a huge number, something that absolutely stands out and catches your attention. So don't worry about the little things, the little mouse that are in there trying to get fed. Focus on looking for that big monster taking a big share, a big bite out of that available voltage. All right, so we check the positive side. Don't have a problem on the positive side. Now we have to check the ground side, correct? And we're just going to do it similar fashion. I'm going to move my ground lead back to the ground side of the battery, as close to that post as I can get. And I'm going to take my positive meter lead and I'm going to connect it to the ground side of the load as close as I can get. And look at that. That's a huge reading, isn't it? That's a big red flag. That's telling you the source of your problem is between here and here. And you know, this is probably the one reading that confuses technicians the most, because I have my meter lead placed on ground here and placed on ground here. How in the world can I measure voltage if both of my meter leads are on ground? That makes no sense. Well, it does if you come to realize that I'm not really on ground here. Let me show you what I mean. Let's go look for that unwanted source. We're going to do it just like we did before, and we're going to move our way back towards the battery until that meter reading returns to normal. Still going. Still going. Still going. See? Okay, we've just passed the point where the problem lies, correct? Now I know that I can move back and forth between those 2 points, where I am now, where I just was, so I can isolate and find the cause of this problem. But here's what I want you to see. Let's go back to that one, that last step. And we're reading, 5.6 volts. We know that's bad, we know that's wrong, but are we truly on the ground side on both leads? Or am I on the positive side of my thief? See, I'm really not on the ground side here, am I? I'm on the positive side of this second source of resistance. And that's why you're getting the voltage reading. That's what's telling me that, hey, I'm going to take that much for myself. And I'm not going to leave that much for him. And that's why he's not working right. That's how that works. That's how voltage drop testing works. Now, again, review this video a few times, get comfortable with the process, make yourself a little bit, doesn't have to be this fancy, grab yourself a bulb, some wire, battery, use your meter, and switch it up. Move that second bulb around somewhere, pick a different type of bulb, whatever you want to do. But get used to what the meter readings are trying to tell you. That's the language you need to understand. And next time on Cardone ProTech, I'm going to show you a real world example and some real common mistakes when it comes to replacing an ECM. Is the ECM really at fault, or is it something else? If you want to make sure you catch that video, make sure that you subscribe and hit that notification bell so you know when it's ready for you. But until then, I'm Pete Meyer. Thanks for watching.